transformative AI and how we're going to get there. So before we start, right, you may have heard of these other, there's a lot of names for advanced AI, right? You've got AGI, ASI, strong AI, all these names. And actually, they're not really amazingly helpful. They're very sort of nebulous. They're not really grounded in anything technical or meaningful or whatever. But transformative AI is in some ways similar, right? Like there's a very big difference between inventing the new internet versus inventing the new agriculture, right? These are different scales of things. But it is actually quite a bit more helpful than the others because it's more impact focused, which I think is actually significantly more important for being able to legislate and govern these new systems. And so for a lot of these things, the how of how we sort of get to these very impactful systems is kind of irrelevant. But we need to have some working definition to talk about transformative AI. Like a lot of these other definitions, there's a lot of disagreement. A lot of research scholars very famously like to quibble over the tiniest of things, and transformative AI is not that much different. So for the purpose of this talk, I've gone for this one by Defoe, which is advanced AI that could lead to radical changes in welfare, wealth, or power. I don't think it's a particularly good definition of transformative AI, but it's zoomed out enough that we can talk about it without quibbling over specifics, right? It's general enough. When we talk about transformative AI, we also almost inevitably hear about superintelligence and things like rapid transformations and all these things. And we're going to sort of cover these a little bit, but I don't think superintelligence is necessarily necessary for AI to be sort of highly transformative. So what does transformative AI actually look like? And I'm going to go out on a limb and say, I think the AI that we already have already fits the definition from the previous slide. It's not superintelligence. That's obviously not, GPT-5. I did make these slides before GPT-5, so with the disappointing update, maybe take this bit with a grain of salt. But yeah, so GPT-5 is obviously not superintelligence. Neither is Claude. Neither are any of them. But I think in the next 5, 10, 20 years, we're going to see massive changes to society, something at the very least similar to what the internet or the computer has done. Why do I think this? Well, partly GPTs, as in chat GPTs, are GPTs, as in general purpose technology, right? They are similar to things like the internet, agriculture, industrial revolution in the way that they touch everything quite equally, that nothing is they're not specialized to specific areas. And I think that if nothing changes from the AI systems that we have now in terms of their raw cognitive ability, we'll have slow adoption, but transformative over a long time period, similar to something like the internet, right? Like the internet comes out in the late 70s, early 80s. Nothing really happens with it for 25 years until all of a sudden we have things like social media and we now can't put our phones down. One way to view this a bit more pessimistically is sort of AI as normal technology by Narayanan and Kapoor, which was sort of published earlier this year, where they sort of take the same view but a bit more pessimistic in that, the fancy AIs that we have now might well just be, something like a smartphone, but, even the smartphone is arguably sort of transformative on a sort of smaller level. So, okay, but how did we get to this point, right? Like what actually has happened? And so we can have this extremely condensed history of AI, right? And we can sort of look at things in two time periods. There's the pre and the post-transformer time period. And the transformer is a specific type of neural network architecture that has allowed us to do a lot of really interesting things, right? So pre-transformer, we were stuck with really narrow AI systems that are sort of tuned for really highly specific tasks. So, AI beat the first human at chess in 1994 with Deep Blue, but that AI system could do literally nothing else. And if you even make a slight variation to the game of chess, where you have an extra queen, it's terrible. Whereas now, ChatGPT is pretty okay at a lot of things, particularly things that it hasn't been trained for. And that's the sort of crucial thing here, that the general purpose nature of the sort of modern AI systems that Christoph was alluding to earlier. Pre-transformer AI was really high performing, right? In some cases, superhuman in the particular domain, but extremely brittle. We're still kind of a little brittle with GPT, the sort of post-transformer world, but they are significantly less brittle. Something that I don't think gets enough sort of attention when we talk about transformative natures of technologies is like how many people are actually using it, right? ChatGPT now has something like 500 million users. So small changes or small developments can have big effects just through reach. Whereas no one was really using AI before the transformer, at least not really, right? Like people had Siri, but that was kind of a toy. I think I say for pre-transformer world, we have clear lines of liability. That's maybe a bit of a stretch. But we had clearer lines of liability than we do with GPT-5 now, right? So what happens when someone uses GPT-5 for something that it wasn't designed to do, but that it can do, right? Like who's responsible for that? So what's actually enabled this shift in what has made the transformer special, right? So the transformer itself is one thing, but similarly, we also have these things that you may have heard of called scaling laws. So let's talk about the transformer first. So they're a neural network. You don't need to understand the specifics so much, like the weird particular architecture is kind of awkward and complicated. But at their core, they're sort of predicting the next token, right? So if you say the capital of France is, it goes into this giant magic box and spits out a probability distribution over words where it's saying Paris with high probability and maybe some other cities with low probability, and then every other word that's possible with a very low probability. Language models themselves have been around in some sense since the 1940s. So what has actually made this special? So there's two big changes that come with the transformer. One is the ease of parallelization. The second is this thing called multi-headed attention. So we'll talk about parallelization first because it's maybe a bit easier to get our head around. So previous architectures for neural networks, like the recurrent neural network and that sort of family, they needed to process sentences word by word. And so what would happen is you would say something like, the cat sat on the mat. You'd go the, and it would then have to predict cat. And you then say the cat, you predict sat, right? The problem is that actually when you're looking at the word mat, to start using the end of the sentence, you have to wait until it has chugged through the whole sentence that you are looking at. This is sort of really inefficient. Whereas on the other hand, with a transformer, you can just put in everything at once in parallel and it looks at them all at the same time. So mat is immediately available for use at the same time as the word the in the sentence. What does this realistically do for us? Well, it means that training is significantly faster. It means that actually you're getting better hardware usage. So your very expensive GPUs that cost $20,000 a piece and you have 500,000 of them, you are now getting like 100% utility versus 10% utility that we would previously be getting. So your equipment is worth it more or is more usable. And it turns out it's more memory efficient, right? So you can fit more stuff on fewer pieces of hardware. So this has sort of allowed us to sort of scale up things much easier. The other thing that they have is this thing called attention, which you may have heard of. But it's one of these vague things that's never really well defined when people say, oh yeah, the transformers have attention, but no one really then dives a bit deeper than that. A full accounting of attention is definitely beyond the scope of the presentation. Even if we had an hour, we would probably only scratch the surface because it's really awkward and complicated. But very zoomed out, right? Like attention is the mechanism by which we get parallelization, just because of the way that the architecture is designed and works. But we also get this improved understanding. So if we consider this sort of contrived sentence again, where the cat sat on the mat, each of these tokens, each of these words, has a sort of a vector here showing how important each of the other words in the sentence is for it to understand what is going on, right? So it's learning to make connections. And so sat here, right, the verb of the sentence is very related to the object, the cat, right? The cat is the thing doing the sitting, and it's sitting on something. And so these are the words that the sort of the model has learned are sort of quite key for the sentence. Now, crucially as well, we have multiple attention heads. What that means is that for each of these words, we have multiple of these attention vectors, which means that what we can do is we can attend to different types of meaning or different types of relationships. So you could have another one of these where what it's doing is instead of looking after the meaning of the sentence, like the cat sitting on the mat, we're looking after the grammatical structure of the sentence. And maybe then the word for the is more related to the full stop at the end of the sentence, because that's giving us some useful information. So the other thing you may have heard of that sort of enabled us, all this parallelization, all this fancy architecture has enabled us to massively scale up AI systems. So what we're looking at here is a plot that you probably can't see the details of, but we are looking at the year from 2010 to 2025, and we're looking at the training compute. So when you do training, we measure this in something called flops. A flop is basically adding two numbers together. And so for Gemini Ultra, we have just reached 10 to the 26 flops. This is an absolutely absurd number, and it can be quite hard to wrap your head around it. It's something like 100 septendillion different additions or different operations are used to train these models. This is actually absolutely huge. You have to note that the y-axis is also exponential, right? So going from, I don't know how well you can see my cursor, but going from, say, here to here is multiplying by 10. Right? So actually, if we don't look at the log plot, it kind of just looks like it's going straight up. We also have these things called scaling laws, which again you may have heard of. And what these say is they sort of pair up the scaling that we have with what we're able to do with the AI system. So what these basically say, again, these are log plots, right? So jumping from the midpoint of this graph here to the end is multiplying by 100. So we're saying whenever we take a step and multiply the number of parameters, the data that we use, the compute we use by 10, we get some fixed decrease in training loss, right? Training loss is bad. It's how much you're screwing up when you're sort of doing the training, and we ideally want to get it as close to 0 as possible. What this is sort of, this is something that was sort of discovered in about 2020, that this has been happening, and it seems to be continuing to hold. So what we're able to sort of say is, well, okay, we know what the next, AI systems are going to look like if we can keep doubling or multiplying things by 10, and that then becomes the question. So you'll also note that most of the progress since 2018, when GPT-2 came out, has actually come from a few key innovations from 2017, the transformer, and 2020, scaling. There are a few exceptions to this. We have reinforcement learning from human feedback, which is used to align the models, make them more better at following instructions, and reasoning. Right? These new reasoning models are sort of able to do some more interesting things. But the core advancement of capabilities has come from stuff from 2017, 2020, and all of the big improvements have come from actually the scaling and improving our ability to scale with improved infrastructure. So even if models stay the same, even if we don't get a GPT-6, things aren't staying the same, right? So there's debate about whether scaling is slowing down, but even then, more things are being scaled. So thinking time is scaling, the number of agent interactions, infrastructure types. What happens in 3 to 5 years' time? So I'm going to sort of end with sort of what could future AI look like. So we're approaching sort of things where we have models with persistent memory, able to sort of plan things longer, agents that act over time, domains more autonomously. We're getting more agents. Embodied AI, once you start putting these AI systems into robots, their ability to interface and interact with the world massively increases. All of these things are like engineering and infrastructure developments. There's no core science needed to have a lot of these changes. None of these are sort of super intelligence, but scaled up, they certainly seem transformative. So the main takeaways I want you to have from this sort of presentation are that, first of all, transformative AI is arguably already here. And we've had a few key innovations, half a decade, 7 years ago, have had massive impacts on what AI looks like today. But progress continues. They're trying new things all the time. What happens when we scale some of these newer things up, like reasoning? Another key thing is that predicting the future is kind of hard. And I think particularly in sort of regulation governance, we've been caught off guard with the rapid progress. And sort of forward-looking attitudes to AI regulation are needed to make sure it's a useful, beneficial technology. And finally, I think the last thing I want to end on is that a lot of really smart people and a huge amount of money are being invested to build these powerful AI systems. And they're not just trying to make transformative AI, they're trying to make superintelligence, they're trying to make God. Maybe we should consider what they're trying to build and take them at least somewhat seriously. 15 minutes is not really enough to discuss this in detail. If you're interested, come chat, come reach out. Thank you.
Great, thank you, Tom.